everyone, welcome to the second lecture of transistors. So in the last class, we basically understood that what is the how the transistor works. So the biggest mistake I made during my bachelor time was that I kept on learning the formulas of transistor, but I was not able to solve the problem. So before IIT Jam, I actually sat down. I understand that how the transistor works. Once you understand that how the transistor is working, then it is pretty much easy game. You can solve any transistor problem. Okay, you only need to know the KCL, KVL, which I will be teaching you tomorrow, in which I will be actually solving the questions of transistor which have been asked so far in the exams. Okay, so today we will complete the theory portion so that our transistor theory portion is done, at least up to that basic of transistor. Now in the questions, many times you will be asked that what is DC load line. So there is an analysis known as DC load line analysis. Okay. So now what will happen is that, let's say I want to find, so I have the graph. Now I have this transistor in front of me. And can you anyone tell me that is what configuration is this? Common collector, emitter, or base? Which configuration is
Common
this?
emitter.
It's a common emitter. So this is your emitter. Okay. So wherever the arrow comes, arrow is coming out. So it is NPN or PNP. You have to know all these things. NPN or PNP?
NPN.
NPN. So whenever the arrow comes out, it is NPN. So it is NPN. And it is obviously common emitter because emitter is common here. And this thing is base and this thing is collector. So what is your input? Your input is base. Okay. So what is your output? Your output is collector. Fine. So now when you draw the output characteristics. So what will be there? So output current, what is output current? IC. So you will see there is an IC current here. And then what is an output voltage? The voltage between base and collector. Oh, sorry, collector and base. Yeah. Or you can say, sorry. This is your output. But in between which two terminals output is connected? It is connected between this C and it is connected between this E. So the output is connected between C and E. This is collector, this is emitter. So your output voltage is VCE. So since in output you have reverse biasing, so your graph will be something like this. It will increase little bit and then constant. Increase little bit, constant. Increase little bit, constant. And this graph is for different input currents. Who is input in this case? Base is your input. So different input currents. So input current is 5 microampere, 10 microampere, 15 microampere. So this is your graph. Looks like. Now, if you carefully see, can I draw this thing? So can anyone tell me, this is an equation I have written in front of you. Can anyone tell me from where I got this equation? Just to see how good you are in electronics. How I got this equation? KVL in which loop?
Output loop.
Output loop. So this is my loop. And now I will apply Kirchhoff voltage law. Kirchhoff voltage law in my output loop. Okay. So just to give you idea, because it will help us in tomorrow's lecture also, I will give you the brief introduction that how to apply Kirchhoff voltage, because it is going to help us tomorrow as well. So it is best that I explain you that how to apply Kirchhoff voltage. So there is one known as closed loop Kirchhoff voltage law. Understand this very well. If you really want to solve the problems which are going to come in digital electronics, in op-amp, in your transistors, Kirchhoff voltage law is very important. Okay. So let's say you have a closed loop. So your loop starts from here. Let's say you get a negative battery. So you get a battery whose EMF is E1. Then you get a resistor. So the value of resistor is R1 and the current through resistor is, let's say, I. Then your loop turns away and then you have another battery here. Now this time you have a positive terminal of the battery. Then you come back and then you have another resistor which is R2. And let's say the current in R2 is in this direction. Let's say it is I2. Okay. And then you come back and you are back to your original position. Okay. So Kirchhoff voltage law says that sum of voltage across all the components, sum of voltage across all the components in the loop is 0. In the loop is 0. Okay. And there will be basically two components in the basic circuit. What will be those two components? One will be your battery and one will be your resistor. And you can clearly see in this circuit, one is battery and one is resistor. Okay. So if you have battery and let's say you are moving in this direction. And first, when you're moving in this direction and you see that there is a positive terminal of battery and there is a negative terminal of the battery, and you have a EMF E1. So if you're coming in this direction and you first see that there is a positive, first thing you encounter in the battery is positive. Then you write minus E. Okay. But let's say you're moving in this direction and first thing you saw is the negative side of the battery. Then you will write plus E. This is a rule for KVL. Okay. Okay. Now, what about resistor? In the resistor, what is the potential across resistor? Let's say the resistor value is R and the current through the resistor is I. Then the potential in this resistor will be V equals to IR. If you are moving in the direction of current, if you are moving in the direction of current, you will apply positive or negative? Tell me. Many of you might know KVL. So if you are moving in the direction of current, positive, negative?
Positive.
In the direction of current, you will apply? Tell me. You're going from higher potential to lower potential. You're going from higher to lower. Should you apply positive, negative?
Positive.
And if you're moving in the opposite direction to the current, so let's say you are moving in this direction, but the current is coming in this direction. Then what you will do? Think from here. When you are going from here, you are going from higher potential to lower potential. In this also, what you are doing? You're going
Negative.
from higher. So here you should apply a positive or negative. Oh yeah, it's a simple KVL.
High to lower is negative, sir.
Is it? So in one direction, your current is flowing like this, and you are also moving in this direction. So you are moving in the direction of current. Then the potential will be V equals to IR or minus IR. It will be plus IR or minus IR. In the second case, so if you're moving in the direction of current, what I remember it is minus IR, right? Isn't it? I'm wrong here. That is what I remember. That is it. If
Right
we move,
here, right.
So that
if
means
we are,
for battery is also same, sir. We are moving from positive to negative. That one also you are getting negative.
yeah, this is negative, fine. This I exactly remember that if you see first positive side, then you get minus E1. Okay. And if I first see negative side, I get plus E. Okay. So I asked you the question, but most of you said IR. Now I am confused. If I am not wrong, so what I remember is if you are moving in the direction of current, you have to apply negative. And if you are moving in the opposite to the direction of current, you have to apply positive. Isn't it? Because in this, you are going from positive potential to negative potential. Right? So positive to negative. So potential drop will be negative, na? Potential has been dropped, na? Change in voltage is negative, nahi? What happened, guys? So if the current is flowing in this direction, so it means you are going from higher potential to lower potential. So higher to lower means your potential has been dropped, reduced. So the change in potential is negative. And if you're moving in the opposite direction of the current, means the current is coming like this, but you are going in this direction. It means you are going from lower to higher, right? So because current is flowing like this in this direction. So this is the direction of current. Means this side is higher potential, this side is lower potential, and you are moving in the opposite direction. Means you are going from lower to higher. So it means potential is increasing. Your potential has been increased. So you will write V equals to IR. That is the concept.
Sir,
Yeah.
Sir, I think both the concepts are right in their place because I have also used the first method in which from higher to lower potential I have used V is equal to my IR, and from lower to higher potential I have used V is equal to my minus my IR. So in so many questions I found answers right. I actually followed that method previously, but now we can also use like this.
But then you have to switch both, na? Then you have to switch this and this both. Then that is fine. That is like taking all the terms from left hand side to right hand side. Okay, so this is the notation. But sorry, I asked you. So battery. So let's say you have a battery, and if you're moving and first thing you saw is the positive side of the battery, then you will apply the minus E1. And if you see the negative side of the battery first, so you were moving in this direction and you saw that there is a negative side of the battery, you will write plus E1. Now, same thing with the current. If you are moving in the direction of current, then you will apply minus IR. And if you are moving opposite to the direction of the current, you will write plus IR. Okay. Now, let's do it in our this question. So now let's start moving from any point. So let's start moving from point A. So if I start moving from point A, so I am moving in this direction. The first thing I saw is negative side. So what I will write? Plus E1. Now I am moving in the direction of current here. So first component is gone. So I have taken the consideration of battery. Now let's go to the second component. What is the potential across this? IR. But now I am moving in the direction of current. It means I have to apply minus I1 R1. Then I am here. Now I moved up. When I move up, now I see the positive side of the battery first. So I will write minus E2. Minus E2 because now I saw the positive side first. So minus E2. Then I am here. And then now I am moving opposite to the current. Opposite to the current. So I will apply
Positive.
plus I2 R2. And finally, I will make it equal to the 0. And now finally, I am back to the A. So this is how I write the Kirchhoff voltage law in the loop. Is it understood, everyone? Even to the basic students, how you write the basic Kirchhoff voltage law. Okay. So that is what I have exactly done. Now you can clearly see this. So now I have this loop. Okay. So now let's start from here. So first thing you see is this battery, and you see the negative of this battery. So what do you apply? You apply the positive. So you write plus VCE. Or let's write our own equation and then we will make it equal to this. So first thing I do is plus VCC because I am moving in this direction and first thing I saw is a negative of this. Okay. And then I am moving here. And what is the current in this resistor? IC. I am moving in the direction of current. So I have to apply negative of IC into RC. Okay. Negative of IC into RC. And then you can clearly see there is a transistor. So I reached till here. Now I didn't taught you that how to do for transistor. That I didn't taught you. So that is very simple. So let's assume this side is positive and this side is negative. Because this will be. Why? Why this side is positive, this side is negative? Because you can clearly see this side is connected to the positive side of the battery and this side is connected to the negative side of the battery. So this side is positive and this side is negative. What is the potential difference between this side and this side? It is already given to you. What is that? VCE. So potential difference between this point and this point is VCE. So when you are coming, what is the first thing you saw? You saw positive. So you saw positive. So I will write minus of VCE and then I will finally make it. I am back to my original position. So I will finally write equals to the 0. So what I can do, I can take my VCE on other side. So if I take my VCE on other side, I will get VCC minus ICRC. So this is exactly the same equation which you are here, which you have it. Is it fine, everyone? How we wrote this equation? If you have any doubt, ask now. Otherwise, no question of transistor you can solve. I can guarantee. If you don't know KVL, not even one question you can solve. Any doubt? I am again asking. Please ask if you have. Okay, fine. If you don't have any doubt, so let's go with this equation. So you all are agree with this equation. Okay. So you all are fine with this equation. So what I have to do? So now what I have to do? So now what is my graph here? So my graph is between IC and VCE. So my graph is between IC and VCE. So I will do a little bit of changes, very small changes. So what I will do, I will bring this on this side. ICRC minus of VCE plus VCC. Or I can say, I will write IC here, minus of VCE by RC, plus VCC by RC. Now, on my y-axis, who is on my y-axis? On my y-axis, I have IC. So this thing is what? What is my IC? My y. What is on my x-axis? It is VCE. So can I compare this equation with y equals to mx plus c? This is a straight line equation where my y is what? My y is IC. My x is what? My x is VCE. So what is my slope? M is known as slope. So what is my slope? My slope is negative of 1 by RC. My slope is negative of 1 by RC. And what is my intercept? This is my intercept. And my intercept is what? VCC by RC. Fine. And this is exactly what you have. You can clearly see you have a straight line graph, straight line here. So you can draw a straight line from here to here. And the slope of this will be minus 1 by RC. It's a negative slope. You can clearly see your line is coming down. And second, what is your intercept? Your intercept is VCC by RC. So your intercept is VCC by RC. So you understand that in my own graph, in my actual graph, my output characteristics, I have now additional line. Can you see that additional line? Is it okay? How do you draw this line? This is known as load line. This is how you draw the load line. So what is the intercept of the load line? What is the intercept of the load line? It is VCC by RC. So this divided by this. If you do this divided by this, you will get the intercept of the load line. Okay. And what is this? What's here? It's only just VCC. Okay. So any problem in this, how I draw the load line? This thing is known as the load line. Okay. This load line will not change. Will this load line change? I can change experiment. Okay. I can do many things with, if my input current is changing, let's say my input current is changing, my transistor characteristics are changing, but will my load line will ever change? If I'm changing my input current, will my load line change? You tell me. This battery is
fixed. Load line depends on the components of VCC and RC, and they are fixed, so it won't change.
They will fix, yeah. So load line is depending upon, you can clearly see VCC and RC, and we have fixed that components. I am not changing that component. So if I change the input current or anything changes in transistor, my load line is not going to change. So this gives me a very powerful analysis method. Very powerful analysis. That is why I draw the load line. So load line is drawn. How? So first of all, I have to write the output KVL, Kirchhoff voltage law. And once I do that, I have to write an equation in terms of Y equals to MX plus C. And if you do that, this is your load line. And this load line is very simple to make. So first make a point here, which is nothing but VCC by RC. And then make a point here, which is nothing but VCC. And then just connect a straight line coming from here to here. That will be your load. Okay. So any doubt here? Any doubt you have? Is it fine, everyone? Okay. So if it is fine, then I want to remind you about the equation that we were doing. So which the equation is VCE equals to VCC minus ICRC. This was the equation which we derived from the Kirchhoff voltage law. Okay. So when the collector current is zero, collector current means output current is zero. So when the output current is zero, your VCE will be equals to VCC. Okay. You can clearly see actually, when your collector current is zero, then your VCE equals to VCC. So this is here. So when your collector current is zero, then your load line is touching which point? VCC. So when your collector current is zero, your load line will touch which point? VCC, which is the battery that you have applied, output battery you have applied. Okay. And in the second case, let's say I say VCE 0. It means there is no voltage needed to go from up to down. So this was your transistor. So this voltage becomes 0. There is no voltage required to go from here to here. If this voltage is 0, if VCE is 0, so if I make VCE 0, this thing 0, then what will happen? My VCC will be equals to ICRC, or my IC will be equals to VCC by RC. VCC by RC. So when my VCE is 0, then at what point my slope, when my load line is touching? My load line is touching at VCC by RC. That is the 2 points. One is intercept on y-axis, one is intercept on the x-axis. And you connect it. That is all about the load line. Okay. Now let's draw load line for one of the questions so that you actually know that how to draw the load line. So the circuit is given to you. and they are saying that draw the DC load line. Okay, why I'm teaching you load line so much? Because in the problems, they will never ask you that find the load line. They will just mention load line, and then you have to know that what is load line in order to move forward with the question. Question will be much more complicated than just finding load line, but you have to know that what is load line, especially in CSIR net if you talk about, and in last 1-2 JAM exams, you have to know that what is load line. So for this circuit, you have to draw the load line. So what is on this axis? You tell me. VCC. And what is VCC? Simply 12.5 volt. So I will take one graph. And on this graph, on the x-axis, I will keep VCE. On the y-axis, I will keep IC. This is my output voltage, which is this voltage. And this is my output current, which is collector current. Simple. Then on x-axis, I already know I have VCC, that is VCC. VCC is 12.5 volt. And on the y-axis, what will I will have? I will have VCC by RC. What is VCC by RC? So 12.5 divided by RC is 2.5 into 10 ki power 3, you will get 5 milliampere. So on the y-axis, I will have 5 milliampere. And then nothing, I simply have to connect these 2 points and my load line is ready. My load line is ready. Just by looking at the circuit, you draw the load line. Fine. Everyone understood how to find the load line?
Hello.
Yeah, please.
Sir.
Yeah.
Sir, ये जो load line है, ये for different circuits, for different values of resistance and VCC, we got a particular specific type of load line for that particular circuit, na?
Yes.
And sir, one more thing I want to just know that we have studied about this load line in our electronics theory in our BSc, MSc, but still we did not get about the main, what is the physical significance of this main load line? Means why do we calculate this load line? What is the need actually?
Reference line. It's a reference line. So load line does not depend upon what transistor is doing. It is depending upon this battery and this resistor. And this battery and this transistor you have applied. So this line will act like a reference line. Okay, so this will act as a reference line. So whatever your transistor is doing, you can actually see that with comparison to my load line, what is changing. Because this load line is not going to change. Transistor, many things in transistor change. With temperature, the beta of transistor changes. With temperature, let's say there is some heating up in the transistor. So transistor get heated up, so its beta change. So its beta change, so all the graph will change. But this load line will not change. Right? Load, why the name load? So very, very good. So you tell me, what is the slope of this? What is the slope of this? Or on what parameter it is depending on? Load. This is known as load. Right? So this line is decided by which parameters? Load parameter. Load resistor. That is why the name load is coming up. This line has nothing to do with your transistor. I have not told you that this transistor is NPN, PNP, what is a beta for this transistor, or what this transistor is doing, so on and so forth. What is my input? What is my signal? Nothing. Only this thing is dependent upon the load. So this kind of gives you a reference line, and you need reference lines. Okay. And then based on that, you can actually compare that with respect to my reference line, how my circuit is fluctuating. That is why load line is important. Okay. Okay. Now there is something known as there is much more applications in electrical engineering. If you go there, everything that they calculate is with respect to load line. Even I was not able to understand what they were doing when I was in the research. They were doing load line calculations a lot. So there was one course I took in my PhD in my first semester, which was analog engineering, analog circuit engineering. Something was there. And then they were teaching that how to do the load line analysis and hybrid model and all of that. And I was not able to understand that why exactly they are doing all of that. But the main reference point, I figured out that it is something which is reference. They are using as a reference. Okay. So whatever your transistor do, that will change your characteristics, but load line will not change.
I have one question.
Yeah, please.
You said that this is a reference line and it will not change, but load line depends on the RC, right?
Yeah.
and resistance depend on temperature
Yeah,
in some sense, right? So if temperature is changing, the load line is also changing.
No, you are in the very back era. Okay, the resistors we are using right now, I can bring it to 1 millikelvin and that resistance will not change. Okay, I can. So the modern day resistors which are coming, which we are using in our electronics, their sensitivity for temperature is very large. You can go. So you think about it, the circuitry which they use when they bring it to the liquid nitrogen, right? It is minus 70 Kelvin. So its resistance should change drastically because those resistors were supposed to be worked at room temperature, but now they're working at minus 70 Kelvin. Sorry, so 70 Kelvin. So how the resistance will not change? So there is a huge amount of, so we were using at 2-3 millikelvins. So at such close to zero temperatures, even if we use our resistances does not change much. Yeah, there was some resistors in the back end era 50-60 years from now which used to change a lot with temperature. That does not happen these days. Heating of the circuit does not rarely change the resistors these days. Okay, so that is not a concern for us. Okay, because we have mastered the engineering of resistors. Fine. Okay, is it okay? Fine. So now there is another thing known as operating point. So now in the circuit, I want you to look at the circuit very carefully. And that circuit is this one. Sorry, this circuit. And now in the circuit, you can clearly see, now let's go to the input side. In this input side, you can see there is a signal applied. But let's say I do not apply the signal. So do you agree that even if I do not apply the signal, this loop is still closed? Do you agree that even if I do not apply this signal, this side is still closed? This loop is still closed. I can go from here, I can move here, I can come back here, and I can finally come back here. So this loop is closed no matter if signal is applied or not. Fine.
सर ट्रांजिस्टर ऑफ हो जाएगा, ट्रांजिस्टर ऑफ हो जाएगा.
Transistor can be off. Let's assume that it is. It can be off or it can be on. So it will be decided on transistor, but it can be on as well. It is not. You cannot be sure that it will definitely be off, because even for zero potentials, you can have the bicycle. For example, you want to bias this, right? So this will be N, P, N, right? So what you have given? So you have made it forward biased, right? If I am not giving this any signal, so this is 0, right? This is 0. So if this side is negative, so can you say that this is 0 and this is negative? So this is forward biased. One side is 0, one side is negative. Means this is higher, this is lower. And this is what exactly you have to do. P should be higher, N should be lower. P should be higher, N should be lower. So you have two ways. Either you make it positive and this negative, right? Or even if I just make this 0 and this negative, still it is forward, because P side is higher and N side is negative. No? Tell me, what do you say? If this side is 0 and this side is negative, so isn't this forward biased or not?
Yes, it would be forward bias.
P side is higher. It is at 0 level. You have no rupee or nothing to give to someone. But this is negative. So 0 is higher than negative. So P side is at higher potential, N side is at lower potential. This is what you want for your what do you say, forward bias. So this is still forward bias. And this is 0 and this is what? This is 0 and this is what? So this is positive, right? So this is 0 and this is positive. So this is higher, this is lower. So this side is reverse bias. So how you are saying that it will be off? On what basis you are saying it is off?
Sir, if this happens, hello?
Yeah.
Yes, sir. अगर ऐसा होता है, if this happens, then the circuit will be in reverse active mode. Means
no. Why?
जो है वो cut off mode में जाना चाहिए.
Why? What is the logic for that? What is the logic for that? This thing is negative, this thing is positive, and this thing is 0. So this is at higher potential, this is at lower potential. So this is exactly what you want, and this is forward biased. This is at higher potential. For this thing, this is at lower and this is at higher. So this is reverse biased. Exactly what we want. Why it will be in reverse? Saturated or anything, any cutoff or any of that sort. So your transistor is properly working, no problem at all. This loop is still closed. Okay, even if your input signal is not there, this thing is closed. Okay.
Excuse me, sir. Sir, I had a doubt.
Only one thing is there. If your battery is smaller than VCE, then it will not be closed. Then your battery should at least be greater than VCE. Then it will be open. Otherwise, it will be closed. Yes, ma'am.
Yes, sir. My doubt was like even if there is no if there is no signal here, no signal, no potential we applied to left side. Does this mean like no current will come out from the base or go in the base?
Yeah, nothing is going. This is zero.
Okay, sir. That's it.
I'm not saying that transistor is working like a transistor. Transistor is working like this. Okay.
So
now,
does this mean that input current and this collector and emitter current are both equal here?
No, that is not really important.
Okay.
Not necessary, because it will have some resistors now.
Okay.
That might be or might not be true. Okay. So yeah, it should be true, but I don't think about that. We can think about that. But basically what I'm trying to say is that if there is a zero signal, let's say your signal is zero. And then at zero signal, the values of IC, which is your collector current, and the value of VC are actually known as the operating point. Operating point, you understand? Operating point means that when the signal is not applied, and now first when you start using transistor, you have to put it to the operation, that it is my operation. Now, if my signal comes, my values will either increase from this or decrease from this. So this is going to be my reference point around which my transistor will work. So the zero signal values of IC and VCE. Zero signal means there is no input is coming up. Nothing you have applied in the input. So zero signal values, whenever the signal is zero, then the values of collector current and the values of VCE are known as the operating point. Let's come to the question. And this is also known as Q point, by the way. And this is being many times in the questions they have asking that what is Q point, or Q point of this or Q point of that. Okay. So this is the question which is in front of you. And that question is that circuit diagram is given to you. And basically everything is given to you. And the first question they are asking is draw the DC load. So first of all, what will be you will have here VCC, which is what? 12 volt. So exactly what I have written correctly, 12 volt. Now, what about here? It is VCC by RC. What is VCC? 12. What is RC? 6 kilo. So this will be 2 milliampere. So exactly this is correct. So DC load line is correct. Now the second thing they are asking that what will be the Q point if zero signal base current is 20 ampere, 20 microampere. They are saying that if I have applied no input signal, in that condition, the base current is flowing. And how much base current is flowing in that situation? 20 microampere. And the beta is given in that case 50. And they are asking that what will be the Q point. So they are basically saying when there is no signal, so Q point, if the zero signal base current is there, but the signal is zero, in that condition, how much will be your, what will be your Q point? What will be your, what you can say, what will be your, operating point? Okay. So how do you do that? You remember this formula? IC equals to beta I. What do you say? Remember this? IC equals to beta IB. Input IB, output IC. How much IB will go to IC? Beta times IB. So IC is beta times IB. This is the formula for common emitter. common emitter. If you have read the common emitter, the formula comes out to be IC equals to beta IB. Very, very important. Very, very important. Okay. So if that is the situation, okay. So then what will be your beta? Beta is 50. What is your IB? IB is given to you as 20 microampere. If you do that, this will be what? 10 power 3 microampere, which is what? 1 milliampere. So IC is 1 milliampere. If IC is 1 milliampere, you remember this equation? Output Kirchhoff voltage in output, VCE equals to VCC minus IC RC. And now basically VCC, what is given? 12. What is IC? You have calculated 1 milliampere. What is RC? 6 kilo ohm. Okay. So what will be you? What is the value you get? 10 minus 6, which is 6 volt. So this is your answer. So what will be your Q point? Your operating point will be 6 voltage and 1 milliampere. So operating point. So if someone asks you that in this situation, what will be your collector current? Collector current for operating this transistor will be 1 milliampere, and operating point for this voltage will be 6 volt. So your operating point or Q point in this question is 6 volt, 1 milliampere. Okay. So this is how you calculate the operating point. Okay. So let me just summarize the formulas, because I thought you are not well aware with the formulas only. So let me just very quickly summarize the formulas for all three transistors very quickly.
Hello, sir.
Yeah, please.
Sir, in last question, there was no signal applied. So how base current came?
Yeah. Okay. First, understand transistor as an individual entity. It's a dynamic component. Transistor is capable of working on its own. You apply a signal or not. So you have a mic. So the current is flowing in the mic. Okay. So when you actually, what you do is, first, when you actually, what do you say? You apply the signal, then you see that your mic starts to, you get an amplified signal. So your transistor without even signal is an active component. It's an active component. But when you apply the signal, you apply the signal in this active component.
Okay, sir.
Batteries are already there. All the batteries are
loop
there.
is closed, right, sir?
Yeah.
It means the loop is closed. This
There is no signal, we can say like this.
Yeah.
Okay.
So actually, the last previous example, you told that this will be 0 volt. That's why my doubt came.
No, I did not. My side applied, but because of this current, base is coming up. That is because of the batteries, the current is coming. Yeah.
Okay, sir. Okay.
Yeah. Battery. Because of the batteries, this current is coming. Because of the signal, nothing is coming.
Yes, sir.
Okay. So that is what is happening. Okay. So let me just very quickly summarize the formula, which is very important in this situation. And that formula is, we have three situations. We have common base, we have common emitter, and we have common collector. Okay. So I will do for these two things because these two are most important. The questions from common collector rarely comes. Okay. So let's do for common base and common emitter. And for common collector, you can look by yourself. It's in the notes completely. In the common base, who is our input? Our common base input is emitter. And in this, what is our input? It is base.
Yes.
And in this, what is our output? Our output is collector. And in this, our output is also collector. Okay. So input current is IE. Output current is IC. Input current is IB. Output current is IC. So what will be the formula for IC in this? Alpha times IB. And what will be the formula of IC in this? Beta times IB. Okay. And what if I tell you what will be the emitter current? My emitter current is always what? ICE equals to IC plus IB. And same formula will be applicable here. Emitter current will be equals to IC plus IB. So in this, what will be the value of IC? I will put alpha IE plus IB. Okay. And in this, what I will do? I will put IC as beta IB plus IB. Okay. So then what I can do? I can bring this up here. 1 minus alpha IE equals to IB. What will be IE? IB will be beta plus 1 IB. So what will be my IE in this case? It will be IB by 1 minus alpha. And what will be my IE in this case? IB into beta plus 1. Okay. And can anyone tell me the relation between beta and alpha?
Beta is equal to alpha by 1 minus alpha.
Beta equals to alpha by 1 minus. That's it. These are the formulas that you have to keep in mind. If you know these formulas, you can solve the problems of transistors. So we understand what is load line. We understood that what is operating point. And now you can actually solve these examples, which are very, very simple examples. You can work on them. I also explained you that how to do your, what do you say? How you apply Kirchhoff voltage. Okay. What does Q point signifies about the circuit? I think if I enter in this domain, I will not come out. Okay. Anyone wants to take on this? Maybe anyone knows much simpler explanation. What does Q point represent? To me, it's a reference point at which we start our transistor. Because in my lab, when I had to start my transistor, my professor said, first find the Q point. And then based on that, select your batteries. Okay. So what do you say? How do you understand Q point? This is my understanding of Q point, that if I have to start my transistor, at what point I have to start? Okay. So that is my base. That is for my. So if oscillations are happening, what is the best point around which I want my oscillation? If my transistor is fluctuating itself, or you can say the point where the load line is, that is also one of the mathematical definition, that is not lab definition. The point where this line and this line intersects, that is also known as Q point, right? This is also one of the mathematical definition, right? That the point where your output characteristics and load line intersect, that is also known as Q point. What is your explanation for? Any other explanation anyone wants to weigh in? Maybe you all are in MSc, BSc. DU has very good equipment for electronics experiments. Many people must be from DU. They have, right? Don't they?
Yes, sir.
The DU is very, very passionate about electronics. I don't know why, but
Sir, what will happen if we operate the system below the Q point?
So the chances that you will lose the control over transistor will be poor, because transistor is going to fluctuate itself. Okay. I'm not an electronics expert. First of all, let me tell you that.
Sir, basically, Q points are the quotient points. Q points are the quotient points, and in laboratory work, we just need to maintain this quotient point in between the DC load line, so that our transistor works very efficiently and very fluently without going to cutoff and without going to the saturation point.
Yeah, so you can either split to this point, or you can either move to this point if you don't maintain your Q point as such. Yeah, this is something. But I am right? Q point is a point where load line and this output characteristics overlap, right? Any electronics expert. I remember an experiment quite back, where we have to find load line, and then we have to find this characteristics, and then we have to draw a graph and then find the Q on the graph.
Yes, sir. Actually, one more use of Q point is there. As you have said that Q points are the intersection between the main graph output curves and the DC load line. So we can also calculate that. We can also draw the DC load line experimentally by using these Q points.
Okay. Yeah. Okay. So from the graph, you can say that where the output characteristics and load line meet, that is Q point. Okay. And this is for the efficient use of the transistor, or you can say to prevent that transistor remains within the amplifier region. Okay. So let me explain this point to here. I think I missed this, but anyway. So if you have your transistor, then the 3 points you have is this thing. Okay. So there is this line you can see, which is being formed. Okay. So if you are in this region, then you say that you are in an amplifier region. If you apply the signal, your signal will get amplified. If you are in this region, or if you are in this region, if you are you will be said that you are in cutoff region, and if you are in this region, then it will be said that you are in saturation region. So there are 3 modes of operating the amplifier. Number 1 will be cutoff, which is basically used for switch. You can cut off your amplifier. means you can stop the current from amplifier. So what will happen? So let's say you press the button, the current is stopped. Now you again press the button, current is on. So now how your transistor is acting? Now your transistor is acting like a switch. So if you want to use your transistor as a switch, which is very much used in your mobile phones, because our mobile phones does not have the digit. Your mobile phone actually has that where they are using the transistor as a switch because it's convenient. You can use transistor as a switch as well as amplifier. So you don't have to put an additional switches in there. Okay. So if you use that cutoff, so in cutoff, what happens is that your emitter based junction and collector based junction, both are reverse biased. If you somehow move to this region, then what will happen? Both your junctions will get reverse biased. If you are in saturation region, both of them will be forward biased. This is also forward biased. This is also forward biased. And if somehow you are, and which is what is most used is amplifier. And if you are in amplifier region, what will happen? Your emitter base is forward biased, but this is reverse biased. This is what we studied. So you see that this is the amplification region. This is the saturation region. And this thing is when your base current is 0. So if you go below that, this region is known as the cutoff region. Okay. That much is enough for the example. Okay. So now let's move to the last part, which is I am explaining this because this is the part of the JEE syllabus. And what I'm seeing from last 2-3 years, especially in GATE and NET, they are putting many questions of JEE because now I started teaching the JEE as well. And then immediately when I see the JEE question, then I realize, oh, this is the CSIR NET question. And then when I see the question of JEE, then I realize, oh, this was asked in the GATE this year. So now I'm feeling that senses that they are asking many of the JEE problems. Because JEE problems are really good. Okay. So in this case, let me give you some two very important characteristics, which is known as voltage gain and power gain. So one is voltage gain and one is power gain. What is voltage gain? So voltage gain is the ratio of change in output voltage, change in the input voltage. So let's say you change your input voltage and then you see how much output voltage has been changed. So let's say I'm talking about most of the times you will be talking about the common emitter because that is the most used transistor. In common emitter, what happens is your input voltage is what? So you are applying your voltage between base and emitter. So if you increase your base emitter voltage, you can see your input voltage is base emitter and your output voltage is collector emitter. So if you change your base emitter voltage and then you see how much your collector emitter voltage has been changed, that actually will give you the voltage gain. How much voltage gain has been happened. Now voltage gain can be written as output voltage can be written as output current into load resistance divided by input current into input resistance. So this thing is known as current gain, and or you can also call it as beta, right? Because IC is what? Beta IB. IC is what? Beta IB. So you can also write IC as beta IB. So this thing will be current gain or current gain in a circuit. Which circuit? Current gain in a common emitter circuit is equals to beta. And this is what? This is resistance gain. This is resistance gain. So your voltage gain is nothing but beta times resistance gain. And these things are usually given to you. How? You will be known. It will be given to you in the circuit that what is your output resistance, what is your input resistance. And based on that circuit, if I ask you that, okay, the beta value of your transistor is 50. Your output resistance is this. Your input resistance is this. How much your voltage will increase? So if you give to 2 volt, how much will be your final voltage? So how much voltage will increase? So in order to find the voltage gain, simply you have to do is use beta multiply by the resistance gain. What is resistance gain? Nothing but output resistance divided by input resistance. Whatever resistance is on this side divided by whatever resistance is on this side. Okay. So this is the formula for voltage. And if someone asks you what will be the current gain, that is nothing. That is simply beta. And all of this mathematics I am telling you for common emitter because that will be the most used. Okay. Then power gain. How much power will amplify? Voltage will amplify, but how much power will amplify? Now you know power is what? Voltage into current. So power gain will be nothing but voltage gain into current gain. And what is current gain? Beta. What is voltage gain? Beta into R output by R. So your power gain will be beta square R output by R. Fine, everyone. These two formulas.
Excuse me, sir.
Yeah.
A minor doubt I had.
Yeah.
Like where is it getting energy for extra power, like power gain?
You are applying battery, man.
Oh, okay, sir. Okay.
Yeah.
Sir,
Yeah.
sir, what is the dimension of gain?
What is the dimension of no dimensions?
And sir, is there any unit?
No dimension, no unit. Gain sometimes are given in decibels, I think, but I don't think so. Decibels it can be given. Intensity gain is decibels, right?
Okay, sir. Thank you, sir.
In dB they can be expressed. dB they can be. Yeah.
I had a doubt, like no matter what the quantity is, if it is initial by final, don't the units cancel anyway, and we just get a pure number regardless of
what is the unit of angle?
Yes, sir.
Angle.
Yes, sir. No angle. Because even in angle, it is arc length divided by the radius, length by length.
So it still has unit, right? Degree and radian.
Sir, in CGS, it is T radian, solid angle.
So angle still has a units, even though it is ratio. Ratios can have units. It does not have dimensions.
Okay.
Dimensions is 0, but it still can have your what do you say?
Okay,
units.
Sir. But they won't have the traditional length units, right? Sir? Length or
no, that will not. They cannot be written in terms of
unit.
They cannot be written in terms of 7 fundamental quantities.
Yes, sir.
That is true. But we give them some name. For example, for angle, we give them radian, degrees, okay, decibels. These things we give them.
Okay. Sir?
Okay.
Yeah.
Sir, RO is the load resistance, right?
Total effective output resistance, man. Output resistance can be of resistor plus your transistor output resistance. Two things. It will be mentioned in the problems. Okay, let me show you any question if you have. I think I have given some question in here where they have actually shown that what is the output resistance. They will mention it. And if they have not mentioned output resistance and then they have just simply given this, then you are safe to assume that this is your output. Then you are safe to assume. Okay. Then you can easily assume that this is your input and this is your output. Then you don't have to worry. But if they have all mentioned that the net resistance net output resistance is this, then you have to use that. Okay. So these formulas, remember, current gain is beta, voltage gain is beta into resistance gain, and power gain is beta square into resistance. These are the three formulas that is very important. Okay. Now they are coming to the point. Actually, what is cutoff? What is cutoff? The point where the load line intersects IB intersects the IB equals to 0 graph. So that is the point. This is your cutoff point. So I already told you that the minimum lower line, the lowest line, this is your IB equals to 0 line. So wherever your load line, and this your minimum graph, smallest graph, the graph which is for IB equals to 0 intersects, that point is known as cutoff. Okay. At this point, at cutoff point, your IB will be 0, means your input gets closed. So now no current is flowing here. This is closed. Okay. So because IB becomes 0. So whenever your load line becomes equals to your load line intersects the IB equals to 0 graph, then it is saying that you are in the cutoff region. And this is your saturation. I already explained you that let's read the official definition of saturation point as well. The point where the load line intersects IB saturation. What is IB saturation? You can clearly see that your load line. So you can clearly see this is the saturation. For first graph, this is your saturation. For second graph, this is your saturation. This saturation, this saturation, this saturation. The point where your load line and saturation line actually touch each other. So you can clearly see for the third line, for the third line, your load line and your saturation line actually touched each other, then this point is saturation. Anything below this will be saturation. Anything below this will be cut off. Okay, so this is how you do. And if you have a normal amplifier kind of thing, you are working in an amplifier region, then how will you represent your transistor? Full transistor. This is your full transistor. Now you are using it as an amplifier. So you have base current, you have collector current, you have emitter current, everything you have. Well, nice. But if your circuit is open, means you are in a cutoff region, then you can clearly see no current will flow. IE will become 0, IC will become 0, IB will become 0. So it's like an open circuit. Cutoff, your switch it is off. Now transistor is not allowing any current to flow through it. And if it is saturation, then input is useless. Then you are what you have actually done, you have directly connected collector to emitter. Direct collector to emitter has been connected, and there is no use of base as such. So whatever signal you keep on increasing, you can keep on increasing your signal, but your transistor will show no effect on it, because now you have kind of short circuited. So you have kind of short circuited your situation. Okay, so that is what happens. So it is an open circuit, this is a short circuit, and this is your normal transistor. This is active or amplifier, this is cutoff, and this is saturated. Okay, yeah.
Sir, what is this significance of this saturation?
You have directly connected your collector to the emitter, means, but now input is useless. Input is useless, right? That means now, so what happened actually is that you are in a region where now the current is going to remain same. IC and IE directly become, they are exactly equal. So whatever input you are giving, that does not matter. That is not going to enter into the region. So basically what you have done is, whatever emitter currents are coming, whatever charge carriers were going from one room to another, now all the charge carriers are going from one to another. So the purpose of transistor has been lost. You have lost the control. The control we had now, that we can tune the base current and we can actually tune this thing. That control has been lost. So this is something, now your transistor is behaving like a wire. Okay, your transistor is sort of behaving like a normal resistor. Transistor is not transistor now, it is behaving like a normal resistor.
Then how will we find this saturation line in the graph, like characteristic graph?
Saturation line in the graph. So this thing you are asking. So they will not ask you to find this as such, but yeah. So wherever you see, okay, so make a load line that you can make. Then you will be given some output characteristics. So you see that for which line your saturation line and load line intersect each other. This. Okay. Or one more thing, which is easiest thing, but I do, and that is almost every book has also given it like this. This is your first graph, this is your second graph, this is your third graph. You can clearly see there is some line being formed. This is the line being formed. And everything below that is saturation.
Okay, sir.
Right?
Yes.
And what is your minimum graph? That is IB equals to 0. Anything below that is cut off. Right? Okay. So let me stop recording here.